In this podcast, we're going to talk about reaction mechanisms, and this is part of 4D. All right, a reaction mechanism is the series of elementary steps by which a chemical reaction actually occurs. The sum of the elementary steps must give the overall balanced equation for the reaction. And the mechanism must agree with the experimentally determined rate law. Remember, that's how we determine rates, is through experiment. All right. So first we have the equation 2NO2 plus F2 goes to 2NO2F. When you're looking at the rate law, you see the rate is KNO2 and then concentration of NO2, concentration of F2. The proposed mechanism is this. So you have step 1 and step 2. The rate of a reaction will be determined by its slowest step. So that first step is going to be our limiting factor to how fast this reaction can actually go. Because once it gets through that first step, that second step will go very quickly. So the first step is really the one that determines how fast it occurs. If you see, F is produced in the first step and then consumed in the second step. Anytime something is produced in one step and then consumed in the next, it's called an intermediate in the reaction. All right, the rate for a reaction can be written from its molecularity, and molecularity is the number of pieces that must come together to make the reaction occur. So here we have a chart. We have the unimolecular, bimolecular, and termolecular. We see unimolecular means that the step involves only one molecule. So this is when you just have one reactant that's forming products. This is going to be a first order rate law, and the rate will just be the concentration of that one reactant. Bimolecular is when you have two molecules required for a reaction to occur. It could be two of the same molecules, so A plus A going to products, which would give you a rate of the concentration of A squared to the second. Or it could be two different reactants, like A plus B going to products, in which case your rate will be the concentration of A times the concentration of B. And both of those are going to be second order rates. Termolecular is rare and it requires three molecules. This could be two of the same, such as two A's or two B's, or it could be three different molecules. So if it was two A's and a B, it would be third order, and your rate would be A squared and then B. If it was A plus B plus C, then your rate would be the concentration of A times the concentration of B times the concentration of C. So this can help us when we're looking at steps. The slowest step is the one that we're going to apply these rules to. All right, so in a multi-step reaction, the slowest step is the rate determining step. We've already talked about that, and that tells us that the experimental rate law must agree with the rate determining step. So when we determine the rate determining step, the experimental rate law that was determined must agree with that step. So here we're given the example of this reaction. The experimental rate law is NO2 squared times H2. All right, so if we're looking at these steps in the reaction mechanism, which one of them is going to be the slowest rate determining step? Well, we know we have NO, and we have that in the first step as a reactant. In the second step, it's not a reactant. And we also have H2, which is in both of the steps. So that tells us that step 1's got to be the rate determining step because that's the one that agrees with the experimental rate law. All right, let's look at intermediates. So which of the species in the mechanism are intermediates? All right, well, here's our two steps, and we see that N2O is produced in the first step and then consumed in the second step, meaning it is an intermediate. All right, let's go back to that first step is going to, that slowest step is going to impede or determine the rate of all the steps. So here we see the first little schematic, Plaza A, obviously gets a lot of congestion there, but as soon as they get past past A, they can go through B very easily. So A determines how fast the cars can travel through these streets. Here, they make it past A very easily, then B is where the traffic jam sort of begins. So B determines how quickly they can get through here. And that's what we mean by the slowest step determines the rate. Once you get past that slowest step, the other one's very easy. All right, another example. All right, here is a reaction. It says the rate law for this reaction is found to be NO2 squared. Well, we see that the rate law, the experimental rate law, does not agree with that balanced equation. Therefore, what that tells us is that this must occur in more than one step. CO is necessary for the reaction to occur, but the rate of the reaction does not depend on its concentration. All right, so let's look at a proposed mechanism for this reaction. Oh. All right, so here's our mechanism. We see that NO3 is produced and then consumed, and NO2 is present in the beginning, present in the end, and then we end up with CO2 in the end as well. All right, so there's always going to be an activation energy for each elementary step. And we know that the activation energy is what determines K. So the activation energy affects K via the Arrhenius equation there. Okay, well, the K affects the rate. K determines rate. So activation energy determines K, and then K determines our rate. So it's really all based on the activation energy here. So we went to look at our slowest step to see what that is, because that's what determines our rate, and the rate determines K, and K determines the activation energy. So the slowest step must have the highest activation energy of all steps. So if we're looking at this reaction coordinate, we see that this reaction has 3 separate steps as evidenced by the 3 separate activation energies there. So we have the first activation energy, which is very fast, a very short activation energy. The second, which has a much higher activation energy, therefore that step is slower because it takes longer for those molecules to collide with enough kinetic energy to overcome that potential energy activation hill. And then the third step is also fast because, again, it's a short little hump there. So the second step has to be our rate determining step because it's the slowest step. Intermediates are present. You see that they are at the base of the activation energy hills in between the different steps. And then we have our activated complexes or transition states, which are at the top of the hills. That's where we're in transition from one state to another. Bonds are being broken and made.